So this is Rusell Cox. I'm the Director of Research at Fletcher Engineering. And my background is in math and physics, and I've only been tangentially watching lunar planetary science over the last 30 years or so. In the last 4 years, I've become very interested, especially since LRO and L-Cross. And so what I want to do in this quick presentation is go back and just look at the fundamental principles and suggest that there may be new things that we have not even yet thought of to discover in very cold craters. So not only is there the lunar science story of cryogenic ices stored in cold trap over the poles, there may even be new chemistry processes, new physics processes that haven't been thought of or haven't been observed yet. So to begin with, back in, we all know, 2009, LRO got there and discovered that the moon was much colder than anybody thought. Some people had been talking about that it should be cold, but most people were simply hoping it would be below 100 or so. Nobody really imagined that 25 Kelvin would be the minimum temperature measured so far, and large terrains down in the 50 Kelvin, 75 Kelvin range. So the moon is much colder and more interesting. We now know that there's lots of evidence, L-Cross proved that there are volatiles as well, trapped. So not only is it cold, it's interesting. So, and my screen has frozen. There you go. So then another example of potentially interesting things is the LAMP results. These are kind of my conjectures from the several presentations I've seen, but it appears that the LAMP results are beginning to indicate that the signal they're measuring is a higher porosity. And that higher porosity is correlated with terrains that are permanently below 50 Kelvin. So this suggests that there really is pericapsule structure or hoarfrost that only exists below 50 Kelvin or so. And so that's suggesting that we may have real evidence that says that different processes occur below 50 Kelvin than even at, say, 100 Kelvin. And we're going to talk a little bit about that. And that's the wrong one. My controls have changed on me somehow. I apologize. I've never had this problem before. All right, so yeah, we're back to, there's the basic temperature of terrain. One of the things that Page and Yang posited before they got there is that the poles of Mercury and the poles of the Moon, you would have complex chemistry. L-Cross proved that complex chemistry exists. LAMP is beginning to indicate that one interpretation of their data is that there are indeed different processes that occur below 50 Kelvin. And then, well, so what's something else below 50 Kelvin or down at 100 Kelvin? And so this is high-temperature superconductors. And so we know what high-temperature superconductors are is an example of a macroscopic quantum mechanical effect. And these effects begin showing up below 100 Kelvin or so. And these are, most of these effects have only been observed in the last 20 years or so, 20, 30 years. Have you really had a convincing case that you can have large-scale macroscopic quantum mechanical effects at relatively high temperatures, 100 Kelvin, 70 Kelvin, 50 Kelvin. And here in this chart we see two different families of superconductors. Now, I'm not suggesting we're going to find superconductors on the poles of the Moon, but what we know about superconductors and many of the macroscopic quantum mechanical effects is that they're controlled by two-dimensional processes. The high-temperature superconductors are layered two-dimensional structures, and all the superconducting happens in that two-dimensional layer. Well, the Moon and regolith is nothing but large and complex different kinds of interfaces and layers and surfaces. And so there may well be, like I said, I would be very surprised if it was superconductivity, but there are other processes that could become interesting and certainly very different than we have observed them so far. Another example of how things change is this is thermal conductivity, and there are many materials that become. If you look on this left side, you see that spike on the left of thermal conductivity, which is at about 40 or 50 Kelvin for most of these materials. So these are aluminum and copper, and different flavors thereof. Interestingly enough, another material that has this property is sapphire. Sapphire becomes essentially a thermal superconductor around 40 Kelvin. And what's interesting here is not so much that these are very high thermal conductivity materials, but what's really of note is simply that the material properties become highly nonlinear. And so again, my conjecture is we're entering a terrain where the physics is different. You might have macroscopic quantum mechanical effects. We know that for many important thermal properties and other kinds of materials properties, they become highly nonlinear. Well, what do we know what happens when things become nonlinear? So nonlinear systems are very different than the linear systems. And so taking research that was done at, say, 150 Kelvin on ices and properties and the type of chemistry that goes on in these ices and transport processes, all at, say, 150 Kelvin, and simply extrapolating them down to 50 Kelvin would not likely succeed in some key interesting cases. So the question is, where might this go? This is an example of last time I was at university in the mid-'80s, nonlinear dynamics was in chaos. It was being discovered, essentially. This is a very simple physics experiment called Couette flow. So you have a cylinder on the inside, a cylinder on the outside, and a fluid in between. And then you have this, you can spin the cylinder on the inside, and you can spin the cylinder on the outside. They can be rotating in the same direction, opposite directions. Very simple system. Even the Navier-Stokes equations, at first glance, don't look all that complex. But what you see on the right-hand side is the phase diagram for the types of stable as well as chaotic flow regimes that you can predictably create. To measure a phase diagram like the one on the lower right takes hundreds, if not thousands, of experiments. And so the conjecture is, if we're moving into a terrain where the physical properties of something as simple as copper have become very highly nonlinear, and this is the type of very nonlinear, very chaotic structures that actually exist in the crystals, we may well be able to discover this phase diagram from Page and Zhang may come to look a lot like the phase diagram in the lower right. Far more complex, far more dynamic, potentially very unexpected properties could be discovered, and they will require extensive exploration on the Earth in facilities that can run 100 samples in a 40 Kelvin cryo chamber over, say, a week or two or a month to let things evolve. And right now, very little research like that has been done. Very few facilities like that exist. And so this piece is, so now we have two key fundamental principles. One, we're moving into a regime where quantum mechanics can become an important key piece in a way that is not normally true at, say, 150 Kelvin. You could study high-temperature superconductors at 150 Kelvin all day long and never guess that they become superconductors below 100 Kelvin. So there may be similar properties that just have not yet been jumped up or discovered in these very interesting terrains. Another feature of why might this be interesting, so why would 40 Kelvin terrain, so if it's going to take a lot of technological innovation and a lot of creativity, a lot of time and money to build these systems. So if you want to build a rover that drives through Cabeus crater at 40 Kelvin and go to try and sample that fluffy terrain that was at the floor of Cabeus, so you've got to build a rover that operates natively at 40 Kelvin, because if it creates more heat, you melt what it is you're trying to observe. Things are going to be very tough technology, very expensive technology to develop, but we now know for a fact that these terrains exist at Mercury, they exist at the Moon, they exist on the icy moons. So basically, the thermal properties at the poles of Enceladus are roughly the same as the thermal properties at the pole of Earth's moon. It's, 100 Kelvin on a hot day and 80 Kelvin on a cold day, and they're probably cold traps that are much colder than that. So we know these terrains are relevant throughout the solar system, and so that makes it interesting science. But that science can also be interesting to, what the people of the Earth want us to discover as planetary scientists. And if you look at the habitable terrains in the solar system, we now know through MSL that there exist or have existed in the past habitable terrains on Mars, and presumably those results will be borne out with more discoveries of similar dry lake beds that look pretty much like Earth lake beds back when they had water in them. And there are almost certainly subglacial lakes on Mars, just as there are subglacial lakes in Antarctica. We know for a fact that on Enceladus and Europa there are icy oceans or water oceans below the surface. We know that there are organic chemicals on the surface of Europa and Enceladus, suggesting that now we have liquid water and organic chemistry. Really interesting results on Titan. There's some, Dr. McKay suggests that there's actually life on Titan literally at 80 Kelvin or 90 Kelvin, methane life forms. I don't know that I would go that far, but let's call it life-like chemistry on Titan. And so if you want to, the Titan Lake mission is going to be floating in a lake that's at about 80 Kelvin, I believe. So to develop these technologies, we're going to need to practice at the moon. To develop the fuel resources we need to get out to Europa and Enceladus and Titan, we're almost certainly going to want to do ISRU. So we want to look at scientific analogs at the lunar poles, and what terrains on the lunar poles exist or could be built that would give you a nice analog for Europa. Ice at 80 Kelvin that you can run a 2 or 3 year long experiment on. You're not likely going to be able to do that easily in a laboratory. So there's again, this suggests that 40 Kelvin engineering, 100 Kelvin engineering has a role and a place for lunar scientists, but no one would have expected this before Elcross and LRO proved that the poles were as cold as 225 Kelvin, and that there is in fact lots of complex chemistry at these very cold temperatures. The LAMP results begin to suggest that chemistry is different at 50 Kelvin than it is at 100 Kelvin. So,
Russell, you have got 1 minute left.
Thank you for that. So there's plenty to discover, plenty to explore, and it feeds into the long-range exploration of trying to find life in the universe. And we now know that places like Enceladus and Titan are not unique bodies to our solar system. Kepler proves that there are billions, most likely, of planetary systems out there, and planets like Europa and Titan are probably far more common than Earth-like planets. So if you really want to understand life in the universe, following those habitats that typically live below the cryogenic environments, or you're going to use cryogenic ISRU to create the fuels to go find them, even if on Mars, for example, you're not doing anything cryogenic, but to get enough fuel to send a lot of equipment to Mars, you're going to be mining it either on an asteroid or on the moon, and you're going to be using these 45 Kelvin terrains. So my talk was simply to try and open up the possibility that there are experiments to perform, technologies to develop that 5 or 6 years ago no reasonable lunar scientist would have really considered as being core to lunar science or lunar exploration or planetary exploration. And I think in the past decade, certainly the last 3 to 5 years, we have proven that this stuff is very relevant. So I'll end with kind of a quick ad. The Space Cryogenics Workshop is one of the sponsors of our workshop, and that's coming up in June. And that's an engineering workshop, so if you want to learn how to build cryo coolers and cryo chambers and things, that's a great organization. We just ran our 3rd Lunar Superconductor Applications Workshop, where we talk about these cryogenic science as well as the cryogenic engineering. We'll be running the 4th workshop next April in Cocoa Beach, Florida again. And I look forward to having many of you present there, both the lunar science, asteroid science, and ISRU, as well as the technologies that could unlock this path to life in the universe. Thank you very much.
Thank you.
Are there any questions out there? Let's see, just wait one more second here, see if anyone wants to type in something. Oh, okay. Thank you very much.